Hello. Yeah. Hello, am I audible?
Yes, sir.
Yeah, so far, now it is okay. Just now it is entering. When you enter the room, it is coming. But it is very slow. Yeah. Hello. Hello. Hello.
Yes, sir.
Yeah, audible, na?
Yes, sir.
Yeah. I think due to some issues, okay, so I was not, means my microphone was also not working here. So hope now I think everything is fine. So let me start. So thank you for your patience. At least you people are there. Staying without hearing anything is difficult task only, right? Hope you are able to see my PPT now.
Yes, sir.
Yes, sir.
Yeah. Yeah. So this is about module 4. Okay. So the title of the module 4 is Digital Transmission through Band Limited Additive White Gaussian Noise Channels. So we are going to discuss about how we can transmit digital data over a band limited channel, and we are considering that channel is an additive white Gaussian noise channel. Okay, means we don't have a channel which is having infinite bandwidth. So bandwidth of the channel is limited. So with that limited bandwidth, how do we able to transmit the digital information, and what are all the challenges? Okay, so first and foremost thing is intersymbol interference. So we are going to discuss in detail about that intersymbol interference. How do we minimize or eliminate that intersymbol interference? What are the different techniques? And all we will be discussing in this module. Okay, So first, let me say about the channels. So this is what I was telling about that. So we can model channel as a linear filter. Okay. So hope you know what is filter, and in that again, what is linear filter. I think so far you might not have discussed it, or we might not have discussed it about non-linear filters, right? So whatever hope you have studied is maybe low pass, high pass, band pass, or band reject filters like that. Am I correct? Hello.
Yes, sir.
Yeah, even in DSP also you might have studied about Chebyshev filter, right? Like that. So is it possible to mention few more names? IIR filter, FIR filters. Yes, is it possible to mention? I am asking. Chebyshev, alternative Chebyshev, what is another one? Butterworth filter. Have you remembered? Butterworth filter. Hello. Hello. ನೀವು ಯಾರು ಮಾತಾಡಿಲ್ಲ ನನ್ನ ಕಷ್ಟನೋ. Akshay was telling yes, at least. What about others? Otherwise, I feel network I have lost or some problem. Please share your understanding of the previous semester. I'm asking, right? I said the channel will be modeled as what? Linear filter with a bandwidth limitation. Why the bandwidth limitation is there? Okay. So the example for this band limited channel, what we can say, one is a telephone channel. So telephone channel, you all know, can transmit a signal having a bandwidth of your voice frequency or at most audio signal, right? Up to 20 kilohertz. And another one is what? Microwave line of sight radio channels. Okay. So then satellite channels, underwater acoustic channels. So these are all examples of band limited channels. So as far as microwave line of sight radio channels and even satellite channels, is it possible to give some examples? So satellite will be means different frequency bands it will be operated, right? So it is limited with bandwidth, fine. Even underwater acoustic channels also. So just let us have an overview of all these different types of channels what I was telling: telephone channel, microwave line of sight radio channel, so then satellite channel, underwater acoustic channels. And you might have come across this Wi-Fi, right? Just to give an example of band limited channels, Wi-Fi will be operated in two ISM bands, right? That is unlicensed band. One is 2.4 gigahertz, and another one is at 5.1 gigahertz, right? Or 5.4 gigahertz. So with a bandwidth of 20 megahertz, and here it is shown, which is a 4G band with different bandwidths. Okay. And so this is all about the satellite channel. Just to get an idea, I've shown this picture. Okay, the satellites are there in different orbits. Accordingly, they will be named as LEO, means low Earth orbits, right? MEO, medium Earth orbit, then geosynchronous satellites. Hope you are aware of these things and how these satellites can be used for communication, right? And to be with this microwave line of sight radio channel, what I was telling, hope you'll be able to see this diagram. So these are the two base stations, what we say. So means one base station and another base station are at line of sight, and they will be communicating over a wireless channel. So that may be at C band, Q band, Ka band. Okay. And this is just about terrestrial microwave line of sight communication, what I've shown here diagram, right? So you all know the Earth is of what shape and how the line of sight has been established. Okay, by installing antennas which are having very large height, and at the top the antennas are connected, so they will be able to transmit and receive signals with line of sight, so that there will be less loss. Okay. Then this is about the underwater acoustic channels. Okay, so here how communication has been established inside the water, right? So by using acoustic signals, how the different devices will be able to communicate. So they're all band limited channels only, whatever I have shown so far. Okay, so now let me just say about, so just I've shown few diagrams to get an idea that, okay, so these are all band limited channels. Okay, so is it possible to say from your end, is it possible to hear? Yes, my dear students, whatever I have shown so far, quickly. Hello.
Yes, sir.
Yeah, is it possible to give the names, whatever I said, band limited channels, examples?
Telephone channel, sir.
Yeah, very good. One is telephone channel. Next one. Yeah, others, please. See, with the diagram when I have shown, I think you should be able to say very quickly. If no diagram, just words, yes, I understand. Huh? Underwater acoustic channel, why this diagram is not attractive? Huh? What about this microwave line of sight radio channel? Is it visible? No? The diagram is visible, right? Hope you
Yes,
are
sir.
able to see these user equipment are nothing but your mobile phones, which are communicating with the base station, right? And another base station, under that there will be mobile stations, we call that as user equipments, right? How these two base stations are communicating, that is through wireless, right? Even there is a backhaul network, right, through fiber also. So there is a fiber backhaul to the core network. And I said about the satellite channels, then Wi-Fi, right? So at least when I'm asking the names, you should be able to mention the different types of channels which we have given as an examples of band limited channels. Okay, fine. As I said, the channel will be modeled as a linear filter, right? So here, what is the challenge is the transmitted signals. Okay, whether I said the digital transmission of data. Obviously, when I say the digital transmission of data, so it will be represented either in the form of zeros and ones, right? And we have discussed it already. How do we represent zero and how do we represent one? That is with respect to different types of line codes, right? Unipolar, polar, bipolar, and Manchester with return to zero or non-return to zero, right? So in each of the line coding, I told what is the advantage and disadvantage also. We have discussed about the power spectrum of that. So you should be able to visualize all that information here to get the picture of, okay, if I say we are transmitting digital data means, so any one of the line code we are using it here, okay? So with that line code, what will be the power spectral density of each of the line code? If you know, then you will be able to visualize whether there will be overlap of the signal as it travels through the channel. Okay, means as the signal is getting transmitted through the channel, it is getting spreaded. Okay, so that spreading leads to overlap of the neighboring signals. That we call it as a intersymbol interference. Okay, so the transmitted signals must be designed to satisfy the bandwidth constraint uh, imposed by the channel. Okay, so as I said already, the examples of band limited channels. How do we say that the channel is going to restrict the amount of bandwidth it can support. Is it possible to say, any one of you, what could be the reason? Say, for example, if I use a copper wire, right, or even optical fiber, so it can pass only certain wavelength, right, not the entire the spectrum. So how does it depends? How do we say that it passes only certain wavelength? Yes, is there any relation to that? Is it possible to find out how the transmission medium, okay, channel is nothing but that, right? How a transmission medium can restrict on the transmission of signal through it. Okay, so just try to find out. So I hope you all will come up with some one or the other answer. Fine. So the transmitted signals must be shaped to restrict their bandwidth to that available on the channel, right? So if I say the bandwidth of this particular channel is say 20 megahertz, if I have a signal which is having more than 20 megahertz its bandwidth, then I need to do something that its bandwidth lies within the channel bandwidth. Then only I will be able to transmit that signal properly, so without any distortion. Otherwise, what happens? It is going to get distorted. So at the end, at the receiver end, you will be able to hear noise rather than the original information. Right? So we are interested in knowing what is the original information, not the noise. Right? So in that way. So as I said, a linear filter, okay, a linear filter channel distorts the transmitted signal. Means I said channel can be modeled as a linear filter, right? So that a channel will be distorting the transmitted signal. So what would be the reason? So with respect to OFC, you can come out with some reason why the signal is getting spreaded as it travels through the medium. Okay. So that channel distortion results in intersymbol interference, right, at the output of the demodulator, and leads to an increase in the probability of error at the detector, right? Because of the overlap of a present symbol with the previous symbols, what happens? The present symbol may be the 0, but the previous symbol may be 1. So the receiver has to take a decision in favor of symbol 0, but because of this overlap, so the receiver may take a decision in favor of symbol 1. Then it will be a wrong decision, right? So with that, we say the probability of error will increase. Okay. So what are the methods and to overcome these difficulties? So that we are going to discuss here. So there are some methods or devices for correcting or undoing this channel distortion. Okay, so those devices or the methods are known as the channel equalizers. So try to keep this in mind. So equalizer, the purpose of equalizer is to eliminate or minimize the effect of intersymbol interference. So that should be there in your mind. Okay, so we'll discuss how do we construct this equalizer. Okay, what is the I think so many things are there under the equalizer, tab and other things. So we'll see that what is the order of the equalizer and all, and what are the different types of equalizers, linear equalizer, non-linear equalizer, and so on. So at least by this point, by this time, you should be able to understand that okay, channel can be modeled as a linear filter. So as the signal travels through this channel, it is getting distorted. Okay, due to that, there will be an intersymbol interference at the receiver side. So that leads to increase in the probability of error. Okay, so to overcome this problem or to minimize the effect of intersymbol interference, so there is a device known as the channel equalizers. Hope I'm clear.
Yes, sir.
Yeah. Okay, so I said no, the channel can be modeled as a linear filter, right? And I said the channel is a band limited channel. Means we can expect this as the frequency response of the channel, right? Because it can pass a signal from minus B to minus BC to plus BC. Okay, or if I say this is the channel bandwidth, what we can say, so which is equal to W hertz. Okay, so its frequency response will look like this. Okay, so this is the frequency response of the linear filter, or what we can say, the channel. Yes, got this point? Means it can pass only certain range of frequencies. That is why we say the channel will be restricting the signal transmission. Okay, only it can pass certain range of frequencies. As I said, channel can be modeled as a linear filter. Means if I model the channel as a low pass filter, what can I say? It can pass only certain range of frequency, right? Say from 0 to 10 kilohertz. Okay, if I consider one-sided spectrum, it can pass up to 10 kilohertz. After 10 kilohertz, what happens? It will be restricting that signal. Similarly, if I say high pass filter, so it will pass only the high frequencies, right? So means if I say it can pass starting from 10 kilohertz, right? Then band pass filter, I will be saying what is that band pass, right? Means from what frequency to what frequency the particular channel can transmit the signal, right? So let us say 10 kilohertz to 20 kilohertz. Okay, so only the signal frequency which are having frequencies from 10 kilohertz to 20 kilohertz, only that will be transmitted. So below 10 kilohertz and above 10 kilohertz, the signal frequencies will be blocked by the channel. Okay. Similarly, band reject filter, if I say, then I can mention, okay, what is the range of frequencies it should be rejected, and rest of the things it will be passing, right? So mathematically, I can express the impulse response, or I can say the frequency response of the channel as like this. Okay, so a band limited channel, example, what I said is a telephone wireline channel, so which is characterized as a linear filter, right, with impulse response, which is denoted as C of t, that is in time domain, and in frequency domain we say it is a frequency response, which is denoted as what? Capital C of f, right? So how do we express that mathematically? So C of f is equal to integral from minus into infinity C of t into e power minus j2 pi of t into dt. Okay, so this is the frequency response of the channel. Okay, so if C of t is the impulse response of the filter, so I am taking its Fourier transform. So the Fourier transform of the signal C of t, we write like this, right? So C of f is equal to integral from minus infinity to infinity C of t into e power minus j2 pi of t into dt. Okay, so what is C of f? Means this is the magnitude response, what I have shown here, the Evode diagram. And second one is the what? Phase response. Okay, so that is written theta of f. Okay, so if the channel is a baseband channel, okay, baseband channel, that is band limited to what? BC hertz. Okay, then the value of C of f will be 0 for the f which is greater than B suffix C or W hertz we say. So which is shown here in the diagram, right? So the frequency response of C of f will be 0 after f is equal C of f equal to when f is greater than BC. Okay. So any frequency components with frequency higher than the BC hertz will not be possible by this channel. So that is why we say it is a band limited. Band limited to what value? Band limited to W hertz, which is equal to BC hertz. Okay. So got this point? What is the impulse response or frequency response of a channel, and how do we express that, and how do we say that it is a band limited? Yes, my dear students, have you got this point? Yes, I did not get any response.
Yes, sir.
Band limited, okay, means only it can pass certain range of frequency. So this is how we write the magnitude response of the band limited channel, and this one is the phase response I said. Okay, so we are interested in more interested in magnitude response than the phase response. So let us see. Yeah. So here, as I was written, W, okay, denote the bandwidth limitation of the signal. Okay, so W is the highest frequency of the signal, I can say. Okay. Even that W is also the highest frequency of the channel with which it can pass. Right? Got that point? So W is the bandwidth limitation of the signal and as well as the channel. Okay, you can think whether it is, you can consider a square wave, okay, of frequency from 0 to 10 kilohertz. So let us assume that the value of W is 10 kilohertz, okay, with a magnitude of 1 volt or even 5 volts also you can consider. And even the channel is also limited to that value only. Right? So I am denoting the input to this band limited channel, right, by this notation G capital T of T. This is my signal. Okay. You all can visualize the signal G capital T of T as a square wave, okay, which ranges from 0 to W hertz, having a magnitude of 5 volts. Then how do we write the output of that channel? Means I am going to transmit that signal through that channel. Channel is also band limited, right, with a bandwidth of W hertz. Then what will be the output of that channel? Already I told what is the how, and we know how the output of the channel and input signal are related. And I said that basically the channel is modeled as a linear filter, right? So output will be what? Convolution of input signal and the impulse response of the channel. So that is what is written here. Okay, so the impulse response of the signal is denoted as C of T, and this is G capital T of T is my input signal, right? So convolution of those two signal will be the output of the channel. So it is a convolution integral here. Okay, so H of T, that is we denote H of T here as the output of the channel. Okay, which is equal to what? Integral from minus infinity to infinity C of tau G capital T of T minus tau into d tau. So it is a well-known and a familiar equation, isn't it? So in short, we denote it with the convolution symbol as this C of T convolved with GT of T. Okay. Hope this equation is clear. Yes, my dear students.
Yes,
I
sir.
said you visualize one box, that is your channel. Okay. And its impulse response of that channel is denoted by C of T. Maybe notations are different. So far, you might have learned that H of T is the impulse response of the system. Okay, I am here taking the different notations. You have to be careful with that. Okay, so C of T is the impulse response in the time domain of the channel, and this G T of T is my input signal. So we all know, since we are modeling channel as a linear filter, so the convolution of input signal and the impulse response of the channel will be the output of that channel, right, or that linear time system. So in the form of convolutional integral, I can express like this: H of T is equal to integral from minus infinity to infinity C of tau GT of T minus tau into d tau. So this is in time domain, right? In frequency domain, what we say, we know this formula, right? Already in frequency means if two signals are convolved in time domain, what will be its equivalent in the frequency domain? So it will be what? Multiplication of their Fourier transform. So that is what is written here. So H of F is equal to, means H of T, its Fourier transform is H of F, right? Then C of T, its Fourier transform is C of F. Then GT of T, its Fourier transform I denote it as capital GT of F. Instead of convolution symbol, I am writing it as a multiplication, right? So this is a well-known formula, right? You are all aware of this. The convolution of two signals in time domain will be equal to what multiplication of their Fourier transform in the frequency domain. So known facts only we are writing it here, right? I am saying what is the GT of f is the Fourier transform of the signal GT of t, and h of f is the spectrum or Fourier transform of h of t, right? Yes or no?
Yes,
Yes,
sir.
anything, any new thing you are learning? Nothing, right? All known facts only, you are putting it in a different way. So thus what we say, the channel alters or distorts the transmitted signal GT of T, we say. Because when we convolve two rectangular pulses of equal width, what will be the resulting signal? Is it possible to say quickly, any one of you have done any time? You take two rectangular pulses having same width, do the convolution of those two signals. So what will be the resulting signal? So at least you take this as your homework. Take width of the rectangular pulse of different value, each one of you. Do that convolution. Okay, so I expect you people to tell the answer on Monday. One day time is there. Do it. And you will be able to understand then how this channel is going to distort or alter the transmitted signal. Right? Understood my point? Hello?
Yes, sir.
Yeah, I said now, take an input signal that is GT of T, okay, is or 2 kilohertz like that. And even take the impulse response of the channel is also a rectangular pulse having a width of 1 kilohertz, same as the input signal bandwidth. Then do the convolution of those two signals. See the output of that, and and you people should be able to conclude that whether the input signal has been distorted or altered or not. Okay, so I think so. Let me stop with this for today. So let me continue on Monday for further discussion.